All right. Well, good morning, everybody. This is our first sort of semi-in-person event, which is very exciting. So we are here to be part of Rachel Bosch's dissertation defense. And that's distracting to you. Dylan just muted. Okay, no problem. So Rachel's committee, who's partially here in person and partially joining us online, includes Dylan Ward, who is Rachel's advisor. And then we have Craig Deach, we have Reza Sultanian, and we have Matt Covington, who is an associate professor of geology at the University of Arkansas. And then we also have Dr. Shaban Abdallah, who is a professor of aerospace engineering here at UC. And there are a number of additional people, both here in person and online, who are joining us today, who are not officially part of the department, but very much are part of Rachel's life. So we have a number of family members. We have several sons. Hello, Sam and Zach and Tyler. Thank you for joining us today. We have Rachel's husband, Aaron Bird, and we have Karen Bird, who's Rachel's mother-in-law. And then online, we also have Rachel's mother and father, Priscilla and Albert. Thank you for joining us today. And we have Rachel's sister, Sarah. And we have some mentors as well who are joining us online today. So we have Will White, who's Rachel's master's advisor. We have Rick Olson, who's been a mentor, Rick Toomey, another mentor. And then hopefully Roger Brecker will be joining us soon. My understanding is that Roger is responsible for getting Rachel back into the academic game after a hiatus and to return to complete a PhD here at UC. So I'm not going to take up too much time, but I do want to just mention a couple of things because we haven't done this in person for a while, and it's a hybrid thing. So if you're online, please do make sure that you've muted yourself so you're not accidentally broadcasting what you're doing to the rest of the people who are also online. And if you're having connection issues, you can always turn off your video. That might help. So Rachel's going to give a 45 to 50-minute talk about the research that's been conducted since they arrived here, summarizing all of that awesome work. And then if you have a question, please hold on until the end. If you're online, you can type it in chat. Zeke King-Phillips is here and helping us coordinate the online portion of this. And then if you have a question you want to ask and you're in person and you are prone to think things through and then forgetting them like me, write it down and we'll make sure we get to all the questions at the end. And I'm going to help coordinate that along with Zeke. If you're a general audience member, you're more than welcome to ask questions after Rachel's done speaking. We're going to have a general Q&A for some amount of time, probably 10 to 20 minutes. And then we're going to have general audience members leave, and Rachel's going to continue to do a Q&A with the committee and also any other interested faculty who really want to go into the more scientific depths of what Rachel's been doing. So if you're on the committee and you have a more involved question, perhaps hold off till the end just so you don't bog down the rest of the audience in things that they might not follow. So we'll do our best to coordinate this since it is hybrid. It's going to be interesting, but it's going to be exciting, and this is really a fun opportunity. I'm really excited to be here today. And I'm almost done, but I just want to mention a couple things. So once we're done, we're going to send out, or I guess Dylan will probably send out an announcement about Rachel's successful defense. So there's, as far as I know, not like a gathering or anything after this, but maybe there is a gathering. I apologize. So maybe Rachel will tell you more about that. But there will also be an announcement if you're not here, so that you will know and you can. And I'm going to let Dylan give a formal introduction because that's what advisors should do. But I will just say it's been a pleasure getting to know Rachel over the time that we've both been at UC together. And I've been really impressed with how involved you've been as a departmental member. And I'm also really excited about the passion you've got for sharing your love of science with others. And I'm really excited to see where that takes you. So without further ado, I will move away from the screen.
See if my head's cut off. All right. prepared some remarks because I haven't spoken off the cuff in front of people in over a year. It's a little more awkward, so don't mind if I read a little bit. So I've served as Rachel's PhD advisor for over 4 years now. They've been an outstanding student. Rachel is creative, entrepreneurial, self-driven, and hardworking. She demonstrates strong teaching, leadership, and community mindedness. Rachel's scientific motivation is a true and deep interest in understanding the physical processes that shape cave passages, sinkholes, and other karstic landscapes, and how these relate to the evolution of surface watersheds. To this end, Rachel has 2 peer-reviewed papers accepted and then in press, a third that's near submission, and a 4th that we'll be working on completing over the summer. To support this work, Rachel raised tens of thousands of dollars in grants during the course of their PhD. Importantly, Rachel's continuing service to Mammoth Cave National Park, Cave Research Foundation, and other organizations, and their outstanding contributions to our department's undergraduate curriculum show that they are equally committed to outreach, education, and conservation. Happy to note that they have recently accepted a full-time lecturer position at Northern Kentucky University starting this fall. It's been my privilege to serve as Rachel's PhD advisor, and I think we all look forward to the presentation.
Okay, thank you, Brooke, and thank you, Dylan. Okay, let me go to the screen and get started. Sure this works. Let me see the right thing. Okay. So we're going to have to, Zeke, talk me through this. Okay. Okay, so I need to change what so I need to stop sharing and reshare. You would think after 16 months of this, I'd have it figured out. Okay, that looks good everywhere? Okay, great. What is that? Which? Right. Right, I'm trying to see how I can get to the, so I can't see the header on here, but now I'll be able to. Now I'll be able to use the pointer maybe, except it stopped sharing all by itself. Okay. We'll try that again. And now it's just showing, okay. Let's see if we do that. Is that good everywhere? Okay, cool. And now I'll be able to get to the the pointer doohickey. Okay. Excellent. Okay, good morning, everyone, and thanks for coming to my PhD defense. So today I'm going to be talking about, can I move that thing? Oh, because it's showing, yeah, sure. So I can make it smaller and then hide it over there. Good. Okay. Okay, here we go. Landscape evolution of the Central. So before we dive into science, it's on. It's not advancing. Laser works. Doesn't work. That's okay. Probably. Yeah. Good. Apparatus. That'll totally reach now. Still need that here. Okay, sorry for all the issues. So let me just move on and acknowledge folks. There we go. Okay, so first I want to acknowledge my family, Aaron and our 3 kids. And here's a picture of us many years ago in front of Mammoth Cave. That's the subject of all this work. And then I want to thank Roger Brucker for provoking me to get back into academia after several years out and getting me to finish my over decade abandoned master's degree and kind of accelerating my interest. And at that point, I decided to come here for a PhD. And so thank you to Dylan for your years of excellent advising, and to my whole committee. And thank you to the whole department. I really couldn't imagine a better departmental community. It's been fantastic being part of this group. And then I want to give a shout out to organizations who provided funding or training or other support throughout my dissertation. And so here's, pretty much a collection of all of those groups. But most of all, the National Park Service and the Cave Research Foundation and Mammoth Cave National Park for working with me in getting the research permit for doing my field work at Mammoth Cave. And then CRF has additionally provided a grant that I recently was awarded, as well as personnel in the field. And last but certainly not least are all of the people who worked in the field before me. There have been millions of people through Mammoth Cave, starting with the late Archaic and early woodland people who were exploring in Mammoth Cave about 5,000 years ago. As you can see on the upper left are the cane reed torches that they used while exploring. And then in the middle is one of the pictographs that was left behind by these people. The earliest historical exploration and maps in Mammoth Cave were done by slaves who were cave guides. So we can see Nick and Matt Bransford on the lower left of this slide. And then I want to call out some of the people who were involved specifically in exploring and mapping the area where I did some of my research. On the top right, we have Leo Hunt and Pete Hansen, who did a lot of exploring in Mammoth Cave in the 1920s and 1930s. And then I want you to make note of the tall person with the white helmet on the picture on the lower right. That's John Wilcox, and we'll be mentioning him again later, back to a map that he drew. And then finally, I need to let you all know that Mammoth Cave National Park sits on lands that have been traditionally associated with the Eastern Band of Cherokee Indians, the Cherokee Nation, the United Kituwa Band of Cherokee Indians, the Shawnee Tribe, the Eastern Shawnee Tribe of Oklahoma, the Absentee Shawnee Tribe, and the Chickasaw Nation, all of whom the Mammoth Cave National Park Administration continues to grow relationships with. So let's take a look at the questions that I've been addressing throughout my research. Overarchingly, I'm interested in how cave passages develop and form, and how the broader karst landscape, both underground and above ground, develops. So what kind of erosional processes are involved in that development? How do the processes underground respond to what's happening on the surface, and vice versa? How do those surface processes respond to what happens underground? And this is a really complex system. How do we explain this to people who can't get out into the field and go see it firsthand? So these are really broad questions, and what I've done is broken this down into 4 more focused questions that I'll be covering today. And this is just kind of a high-level sampling of what I've done and the work that I'm continuing to do. So the first topic we'll be covering is chapter 2 in my dissertation,
which is an erosion modeling project. And here I'm asking the question, does karst abrasion lead to scallop tunnels? And then we want to validate that model using field research. And so we're asking, what is the erosion rate of a scallop cave passage floor, which is the type of surface that we're modeling in chapter 2? And what can we deduce from that erosion rate about the processes that may be involved in the development of the cave passages? We then switch over from erosion to deposition, and I'll be discussing a large sediment deposit in Mammoth Cave and asking the question, what series of geologic events led to the deposition of this pile? And then the final topic pertains to teaching. How do we communicate these concepts to people, and particularly to people who cannot get out to the field? So let's dive into question 1. No, you know what? Let's back up a little bit, and I'll give you a little introduction to karst landscapes. So karst is generally a landscape where you have soluble bedrock underlying the surface. And so this provides an opportunity for the water to preferentially enlarge conduits underground. And so then you have your water flowing in the subsurface much faster than other groundwater and focused into this conduit flow. And you have a lot of surface features that are particular to karst landscapes, like sinkholes and vertical shafts and springs. So if we look at the a critical zone kind of approach to this, the critical zone is the zone ranging from the top of the trees down through the water table. And the critical zone in karst, it tends to be on an order of magnitude greater or deeper than critical zones in silica bedrock. And the focused nature of this conduit flow allows both water and pollutants to get into the subsurface more rapidly and to come back out to the surface more rapidly. So getting into the first focused question, does karst abrasion result in scallop tunnels? So here I'm building on this seminal paper by Bloomberg and Curl in 1974, where they did some bench scale experiments and dissolved these scallops out of a block of gypsum or plaster of Paris. And so they were able to see that these bedrock forms could arrive by dissolution, and they presented the results that the average water velocity up above the boundary layer, the scallops, is inversely proportional to the length of those scallops. So when you have much shorter scallops, your water is slower. When you have much larger scallops, slower water, smaller scallops, faster water. Okay. And they also provided a set of parametric equations which gave us the general form of these scallops. And so I've enlarged that at the bottom, highlighting the different regions that I'll be talking about through this project, particularly the lee side, just downstream of the crest, and then further downstream, you have the trough and then the stalks. So if you look at all of these scallops, you can see that they tessellate this limestone bedrock inside of the caves. And you also might notice, particularly in this one on the left where I have ZAC for scale in this little tunnel, there's sand on the floor. And so you do see plastic sediments near scallops in caves, and sometimes right in scallops on the floor in caves. And so then that led me to want to question and test this basic assumption that scallops rise exclusively from dissolution. Perhaps there is a role for abrasion here. And so that leads to the question, does karst abrasion result in scalloped tunnels, which provided us with the acronym that Aaron came up with, DKarst, for our numerical model. So our hypothesis here is that there are 3 different phases of erosion. So there would be conditions under which the scallops are arising and maintained exclusively from dissolution. There could be conditions under which they're arising and being maintained exclusively by abrasion. And then there may be a set of overlapping conditions where both abrasion and dissolution are contributing to the development of these scallop forms. And then there's the opportunity there for some interesting feedbacks between those processes. So this is the general structure of our numerical modeling approach. We used the parametric equations from Bloomberg and Curl for our scallop shapes. And we took those along with the velocities from Bloomberg and Curl and used those to perform some computational fluid dynamics simulations, which gave us the overall water flow field through that whole region. We then put the flow field along with the initial conditions from Bloomberg and Curl into a Python code that Dylan and I developed. And then in here, we calculate the particle trajectories and the particle velocities, the impact locations on the scallop profile, and then use all of those to estimate erosion rates. And I'm going to pass around a little block of salt for you all so you can get kind of a hands-on feel for scallops while we're doing this. So here are the results of the computational fluid dynamics simulation. On the bottom left, you can see the computational grid that we had, and the grid spacing on here is the same as what we have on our Python simulation. So that makes it easy to take this data and then import it into Python. And then you can see the velocities themselves in these contour plots. The one on the top shows a sample of several scallops, and you can see how the scallops perturb the flow just at the bottom or in the boundary layer. And then up above that, you have a uniform flow that is equal to the Bloomberg and Curl equation. And on the bottom right, we zoom in on just one scallop. So you can see how you have these focused high velocity areas at the crests, and then this very low velocity region in the lee side of the scallop. And take all this, we put it into the Python code, and here are some of our results. These are sampling of trajectories of particles as they move through the region over 4 different types of scallop profiles. So each of these pertains to a length of the scallop. So on the top right 3 plots, for instance, you have a region of 1 centimeter scallops, and on the bottom right are 10 centimeter long scallops. And so you can see some of these, the particles are deposited very quickly after they enter the region, and in others, the particles are transported throughout the entire region. And so here we can see as a function of the size of the particles, and the length of the scallops they're being transported over. How long are they transported over each set of scallops? And broadly, as the scallop lengths increase, so from top to bottom here, with blue being 1 centimeter scallops, red being 10 centimeter scallops, our water velocities slow, and therefore the particle travel distance is also shorter. And then the particle travel distance is also longer for small particles, and then as the particles get larger, that generally decreases. So we're able to take this data and then use this to provide a set of erosional estimates, erosion rate estimates. And so in this plot, we have the same 4 colors for the scatter plot again, with 1 centimeter scallops in blue dots and orange dots for 2.5 centimeters, green for 5 centimeters, and then red are the 10 centimeter long scallops. So I've plotted the erosion rate over these scallop forms as a function of the grain size. This is compared with dissolution rates from existing publications. And so here we have simulations done using computational fluid dynamics by Hammer et al. In 2011 and Godam et al. In 2017. And both of these teams modeled the concentration of calcite ions at the scallop surface and then used that to calculate the erosion rate that they would expect at the surface. And so the lower end of each of these bands is from Godam et al., and then the higher calculated dissolution rates are from Hammer et al., with the bands again having the highest dissolution rate with the fastest water over the 1 centimeter scallops, as you can see by that broad blue band at the top. So what we were looking at in that previous plot was just the lowest sediment concentration that we might see going through a cave river at 7 times 10 to the minus 6. And so here I've plotted what we would expect those compared abrasion and dissolution rates to look like at 4 different sediment concentrations, increasing from left to right and from top to bottom. And as we would expect, as you increase in sediment concentration, the abrasion becomes increasingly dominant over the dissolution. So let's look at this in a little bit of a different way, where we're kind of summarizing this information and directly comparing the dissolution to the abrasion. So what I'm plotting here is, on each of these plots is one of those scallop lengths. On the vertical axis, we have our sediment concentration. So that's going from low concentration at the bottom to higher concentration at the top. And then the horizontal axis is our grain size. And the colors here represent the percent change between abrasion and dissolution. So anything that falls within those dissolution bands that we saw on the previous plots falls between negative 39 and positive 39% change, and so would be represented here by the yellow bands. And so those are regions in which we would expect abrasion and dissolution to both contribute. The blue areas are dissolution dominated, the red areas are abrasion dominated, and the results we're seeing here assume that all the particles that hit after the 3rd scallop would contribute to the abrasion, which may not be the case because we might have things that are depositing there. So if we look at all of the particles that get transported further than a meter, our distribution here changes a bit, and we see a lot more dominance of dissolution with a narrower band of overlap between the dissolution and abrasion, a smaller area of abrasion dominance in the 5 centimeter scallops, and then the 10 centimeter scallops, it's completely dissolution dominated by this. And so if we put that all onto one plot, we're looking here with our horizontal axis is our scallop length, which can also be seen as a proxy for the average water velocity, as was discussed earlier. And so we have scallop length increasing from left to right, which is water velocity decreasing from left to right. The vertical axis, again, as in the previous plot, is sediment concentration. And then going back into the screen is the ratio, that's a dimensionless ratio of the grain size to the scallop length. So we can see all of the low concentration areas are dissolutionally dominated. We have a middle range of concentration where there may be an overlap between dissolution and abrasion. And then in our high concentrations, depending upon the scallop length and the grain size, we have some areas that may be dissolutionally dominated or abrasionally dominated, or they might be completely depositional, and so then the bed would be armored against erosion. So I decided to plot some sediment concentration data from a couple of field studies on here. One from Logston River and Mammoth Cave, and another from Arch Spring, which is the resurgence for Tytuna Cave in central Pennsylvania. And particularly that high sediment concentration value for Arch Spring was recorded during a hurricane. So it really is likely a high concentration value for a karst river. And granted, it's only 2 data sets, but they both fall within the bottom half of this sediment concentration range. And so it's looking like we might not often see a role for abrasion in cave scallops. And so our conclusion, based on that previous mechanochemical phase plot, is that there are 5 different regions based on conditions that we might find in caves. We would find a dissolutional zone. We would find that overlap zone where the abrasion and dissolution both contribute. See 2 different abrasional zones, one for smaller grain sizes that may maintain scallop forms and contribute to their development, and then an abrasional zone with larger grain sizes that would likely destroy any scallop bed forms that are on there. And then we have a 5th depositional zone. So I would say that these results do support our hypothesis, because we do see the 3 zones that we originally proposed at the beginning of this project. It was expanded to add 2 phases. So we do see a likely role for abrasion, but maybe not a significant one. So when we compare our simulation results with field data that's already been done, it really reinforces the paradigm that cave scallops arise and are maintained predominantly by dissolution. So I just wanted to revisit one of these neat trajectory plots that we made. And so the scallops in there are all exactly the same size, and they're all in one neat straight row, and they're 2-dimensional. So we can learn a lot from doing these simulations, but we really need to validate this with real world data, because here on the bottom, you see a rock on a cave floor, and it has scallops, but it also has some little things that look like incipient potholes. These scallops are a few different sizes, and they're they're not arranged all in one straight line. And so this leads us to develop a micro erosion meter study. And so this is taking place in the Roaring River at Mammoth Cave National Park. And let me pause for just a moment. So Roaring River, the level of this river fluctuates quite a bit. It's a direct tributary to the Green River, which is the base level for all of Mammoth Cave. So we're able to determine if it's safe to go to Roaring River by looking at USGS gauge data at the Green River, both at Mammoth Cave Ferry and a little bit upstream in Bunkerville, Kentucky. And so this area, which we go to check the erosion sites, is down this sandy slope, and then under the ledge to the left, we hike upstream for a little bit, and we get to these stations. And this is this passage is available for humans to go into about 40% of the year. If you look at the hydrograph in the upper right, there's an orange line noting the stage at which it's not safe to go above that stage. It's pointed out with the orange arrow as well. So here's the passage that is sometimes full with Roaring River. And I like this picture mostly because it gives you a sense of how large this passage is. And sometimes it's completely full to the ceiling with water. And the ceiling itself has some marks on it that look like they may have been caused by rocks banging across the ceiling as they're transported through. Again, motivating this research on abrasional processes. So this is what the station looks like up close. There are 4 of these stations in Mammoth Cave, and I brought with you a representative sample of one of these. So, okay. So this is limestone. This is not from inside of Mammoth Cave. This is a rock from it's actually from Claremont County, Ohio. Just testing out how this station works. So here we have, we drill a set of 6 holes into the rock. There are 3 stainless steel pins that are flat on the top, and then 3 threaded rods. We have these templates that were designed in conjunction with Matt Spetz, the 1819 Innovation Hub at UC. This template sits firmly on the 3 rods on the 3 pins. There are little pockets that the pins go into, and there are holes that the rods come through, and we secure that on with wing nuts. So it's at the same elevation every time we install it in the cave. We put a depth micrometer in this slot in the top and measure the distance from the plate to the bedrock. So as the bedrock erodes, that distance will increase. And from that, we can calculate the erosion rate. So we have a little over a year's worth of data. It's been challenging to do field work during the pandemic, and as I noted, it's very weather dependent to get down there. So hopefully there will be some dry time this summer to go down and get a new set of measurements. So the numbers that we have thus far are inconclusive as to the erosional rate. They all fall within human measurement error at this point. So now let's move to a different area of the cave. We're going to stop talking about erosion for a while. We're going to talk a little bit about deposition. So this is chapter 4 in my dissertation. It's debris flow in Mammoth Cave, field characterization. This, everything I'm covering in this section is in a paper that's impressed with co-authors Dylan Ward, Aaron Bird, Dan Sturmer, and Rick Olson for the Journal of Cave and Karst Studies. So deep inside of Mammoth Cave, more than a mile from any currently known entrance, there is this really large pile of siliciclastic sediments. So these are almost 100% sandstone sourced from the Big Clifty that's up above, sits above all of the carbonate rocks in Mammoth Cave. And you can see that some of the largest rocks in there are up to 1 meter in diameter. And then if you look at the ceiling, which is consisted of the Joppa layer of the St. Genevieve limestone, it's really smooth. And so there's no way that these rocks could have broken down off of that ceiling. It's a different kind of rock and the ceiling's really smooth. So how did they get there? Cavers speculated that these rocks were transported in by a really huge flood. And so they named this feature Mount Ararat. And the passage that goes off to the right, so if you were to walk straight ahead in this picture, you'd be in Big Avenue, and if you take a right, you'd be going up Noah's Way. So Mount Ararat is almost entirely in Noah's Way and then comes out into Big Avenue a little bit. And looking at these rocks, we've hypothesized that this has been deposited by a debris flow that entered through the southern end of Noah's Way and through an entrance in Doyle Valley that is now completely obscured. So to test this hypothesis, we did some surface investigations using maps and GPS. We did some sedimentological work, looking at the grain size distribution of the pile. We did a 3D imaging project where we used LiDAR to look at the surface of the pile, and then we used near surface geophysics to get an idea of where the bottom of this pile is. So on the left is a map by John Wilcox. If you remember back to the person in the white helmet on the in the acknowledgement section, and you can see some of the large rocks at that intersection. Make this work. We'll just use this as is. So some of these large rocks are at the head of Mount Ararat, and then if you come back down through Noah's Way, you can see this slope, which is also Mount Ararat, and then the tail is around about here. There's a passage that goes down to the east that has a little bit of water flowing in the bottom of it. And then if you continue south in Noah's Way, there's a location that says borehole directly above. And so this metal borehole, which you can see in the passage, we used a combination. How do I make this be quiet? Okay, that'll just have to go away on its own. We used a combination of a GPS app and a smartphone, along with topo maps and geologic maps, and we located this borehole on the surface, which was really neat because then we could stand there and look out over the surface of Doyle Valley, and we knew that we were right above Noah's Way, and weren't able to see any expression of any cave entrance there on the modern topography. This slide covers how we did our grain size analysis for Mount Ararat. So we used a combination of sieving sediments with a sieve shaker from 3 samples taken of the matrix material of Mount Ararat, and then we used a grid counting method like you might do with thin sections on a microscope, but here we used a photograph of this cross section of Mount Ararat and gridded it off to note the grain size in each square. And so about 30% of this is the fine matrix from the sieving, and then the blue portion of the graph is what we captured with those larger grains in the grid counting. So the story behind the LiDAR is really neat. One day on a road trip, Aaron and I were passing through Georgia and stopped at Bass Pro Shop, where a stranger approached us because he liked Aaron's caving t-shirt and introduced himself and said, you know, I work for this surveying company and I've always wanted to do terrestrial LiDAR in a cave. So we said, well, you know, we might be able to help you with that. And so Abby Kelly, who's in the audience, helped out on that project. And we met up with Tate Jones and his crew and surveyed Mount Ararat. The resulting point cloud in the upper left has over 2 million points. And then on the left center, you can see the surface mesh that we made with that point cloud. The Mount Ararat and the trail are in tan, and then the bedrock of the cave passage is in that silvery blue color. And if you compare that with the photograph below, you can see how well the LiDAR survey captures this surface. But, oh, there we go. But this is in a really sensitive area in a national park, and we still don't know what's underneath, and we can't dig trenches into it. So here we turn to electrical resistivity using Reza Sultanian's electrical resistivity setup. Dan Sturmer came out in the field, and we were able to set up one array of electrodes in the cave. You get to haul this big car battery a mile through the cave. And that gave us 7 different resistivity points as a function of the depth that you get when you make these semicircles connecting the different points in that array that you see on the left. Those are then interpreted, since each of these is traveling through these different layers as you go down. You need to use some modeling software to kind of parse that out and separate it into the resistivities that are estimated for each layer. And so those are in orange in the center plot. And we interpret those as being the top 0.25 meters below the trail as being trail surface material, which is sand that's been transported from different places and used to build the trail. Then from 0.25 meters below the trail down to 0.75 meters below the trail, this is interpreted as debris flow material being part of Mount Ararat. And then below that is the buggy limestone floor of the Big Avenue Passage. So we were able to put that all together, the surface LiDAR shape of Mammoth Cave, of Mount Ararat, along with the interpreted floor from electrical resistivity, and then we digitally cut out the pile itself. Additionally, again, through the wonderful 1819 Innovation Hub, they have a bunch of 3D printers you can use. We were able to print out a copy of that surface, and there's a little scale bar on there, so you can kind of touch it and imagine what it might be like, I guess, if you were a mite crawling around on Mount Ararat. And so using this cutout volume, we're able to calculate the present day volume of Mount Ararat as being approximately 3,400 cubic meters. The distance from the tail of this debris flow deposit around up to the head is 75 meters, and then the thickness of the deposit at its highest point is about 7.5 meters. So another way to view this data is like a digital elevation model. So we also took that point cloud data and viewed it in QGIS and interpreted it like a landscape. So here we have a series of profiles along Mount Ararat. So let me pull up this pointer again. We can just use the pointer. So this one major profile labeled P goes all the way from the tail along the spine of Mount Ararat and up over the head and back down to the passage floor. And so here on the lower left, you can see a cartoon of a typical debris flow deposit. And so you have this big head of material that, if you imagine this debris coming down, it's kind of fluidized. It's this mix of all these different grain sizes. And the largest grain sizes kind of raft and float to the top. And so you can see that boulder accumulation in the head of the debris flow, and then it tapers off into this tail. And so we can see that Mount Ararat really looks like not just one debris flow, but indeed two debris flows, with the first head being here, and then it comes off and tapers back down to a tail that's buried down beneath the second debris flow, which has its head here and then tapers back off this way. A few other cross sections that are worth pointing out here. Cross section A, each of these is going from the west to the east. Cross section A shows that base that we used for grain size analysis, where the entire thickness of Mount Ararat has been eroded through. At cross section C, you can see it's kind of flat. That's the saddle that's just past the head of the second smaller debris flow deposit. And then cross section D is kind of neat. It has this little divot over on the eastern side, which corresponds to a little channel that's now completely dry all along that eastern side. So we synthesize all of our interpretations for this in the form of a geomorphic map, where you can see the first larger debris flow would have been deposited first, and that's outlined by the heavy dashed lines. And then two events happened after that, for which there's not any stratigraphic evidence to say which one happened before the other. We had a smaller debris flow deposit on top of the large one, and we had this erosional event with this small channel that comes along the east side. And finally, we had this fluvial erosion down into the side passage on the east that cut through both the large and small deposits. So here, the results of this field work support the interpretation of Mount Ararat as resulting from debris flow deposits that where the material was sourced from the surface in Doyle Valley and then entered through this hypothesized entrance that we have on the map on the right. Our work enabled the calculation of the current deposit at 3,400 cubic meters. And we estimate that through that prior to the erosion events I just covered, that the original deposition was more than 3,800 cubic meters in these two debris flow surges, then with more than 400 cubic meters removed in subsequent erosional events. So now it's time to leave the cave, and we're going to entirely kind of switch gears now, and we're going to be looking out at the whole world for a moment, and then talking about a digital field teaching experience. So this paper, Development and Implementation of Virtual Field Teaching Resources, is impressed with geoscience communications. And it's based upon a curriculum that Aaron and I developed for in-person presentation. We were going to be teaching the Karst geomorphology class at Western Kentucky University for their Karst Field Studies program last summer. And when that was canceled, it coincided with several other field camps being canceled, and that's when the National Association of Geoscience Teachers, in combination with the International Association for Geoscience Diversity, brought together a lot of people in the community to develop these virtual field experiences so that we could provide those kinds of learning opportunities for students who couldn't do field camps last summer. So on the left are just a sampling of the objectives that we developed for our in-person field camp, and then how those were pivoted to this virtual field activity. So I developed two activities as a part of this effort. There's an introductory Karst activity and a more advanced Karst activity. Both of them are available on the Science Education Resource Center that's maintained by Carleton College. The advanced activity needs to be done on a laptop or other computer, whereas the introductory activity can be performed either on a laptop or on a mobile device. So in both of these activities, students first start by selecting a karst area that they want to explore. For the duration of the activity, introductory students are given a sampling of 7 different locations in 7 different places throughout the world, and they have the Google Earth links to go directly to these places to start exploring. Whereas in the advanced activity, students are given the World Karst Aquifer map and then expected to choose an area to focus in and then go to Google Earth to start looking at that place in more detail. So here we are selecting an area in Mexico near San Luis Potosi, and we're going to be looking specifically at the karst area right around the cave called El Sótano de las Golondrinas. So if we look at this area in Google Earth, and so here students can get an idea of what the landscape looks like. They can get access to photographs and descriptions and just kind of get an idea about what it might be like to go there and to fly over there. And they can grab the geographic coordinates right from Google Earth and then take those over to the Earth Explorer website through USGS, where they can get digital elevation data. They then take that into QGIS and reproject it to the right coordinate system. And they apply colors according to the elevation of it and extract a hillshade layer so that they can have a good visual representation map of their area. In the advanced module, students also add a geology layer on top of this. Sometimes you can find these digitally that you can import directly as like polygon shape files and things like that. For Golondrinas, I had to go back to a 1968 Association of Mexican Cave Studies journal and found an analog map. And so the activity also does walk students through georeferencing analog materials in QGIS for the advanced activity. In both activities, they then extract elevation contours from their data, and then they're going to use the rule of B's to interpret where water would flow over the landscape. So this is as far as the introductory activity gets. And so then students can form some hypotheses about what kind of natural hazards might occur in this landscape, or what particular environmental vulnerabilities that landscape might have. And they present their results to a cohort if they're working with other students, and also in writing to the instructor or mentor they're working with. The advanced activity continues on to use an automated flow routing algorithm called topographic analysis kit. And they compare their results from the manual and the automatic flow routing, which here you can see they're really quite different for this area. So then students are prompted to address if their results are different, why is this? And then they synthesize their results and are asked to propose some hypotheses about why this landscape might have come to look how it is, or about something else they will want to learn about this landscape, and they develop a proposed experiment using field work or using further digital analysis, and specify what kind of data they would need to collect and how they would collect it to answer their questions. So there were many activities developed as part of this effort last year. And in order that these could be used for students to satisfy capstone requirements coming out of undergraduate geology studies, I assembled them into 3 different capstone pathways. And then these are geared towards 3 potential broad areas of interests that students might want to pursue. So they could do a virtual field camp on planetary geology, which you right now couldn't do in person anyway. Or they could do environmental geology, or they could take a more traditional approach. So each of these has an equivalent completion time that's estimated to approximate a traditional field camp, along with a progression from more basic to more challenging opportunity or activities as students build skills throughout the course of the activities. The pathway on the right, traditional geology, was offered at UC in the spring of this year. Dan Sturmer facilitated instructing that class, and I had the good fortune to speak with one of the students who took this class, who said that he felt like he really learned a lot, and he liked how the activities built one upon the other. Like, he really felt like that, you know, he got skills early on that he needed later. And while this can't substitute for a field camp experience, it also has the advantage of being accessible going forward and providing exposure to some digital tools and software that students might not get in a field camp. So here's a little summary of the questions that I have addressed throughout my PhD studies, and then the answers that I've described to you, these questions. So does karst abrasion result in scallop tunnels? And the answer is sometimes it might, but under most circumstances, dissolution is likely to be the dominant process. And what is the erosion rate of that type of scalloped cave passage floor? And we're still waiting on years more of data before we can give an answer to that one. What series of geologic events led to the deposition of Mount Ararat inside of Mammoth Cave? And here we have concluded that there were likely at least 4 discrete events that contributed to Mount Ararat as we see it. 2 surges of debris flow deposit, depositing more than 3,800 cubic meters, and 2 subsequent erosional events removing more than 400 cubic meters of the original deposit. And finally, how do we communicate the complex field concepts of karst hydrology and geomorphology to students who cannot get to the field? And here I've concluded that virtual field experiences activities, they're effective and accessible alternatives to field camp, not a substitute for field camp for students who want to and can get to the field, but they're valuable learning experiences and can provide exposure to important tools in our increasingly digital discipline of geology. And so with that, I would be happy to take any questions. I would suggest. Which is possible. Yeah, the posts themselves could will definitely have some effect on the flow, but when we look at the CFD results from the scallops, there is flow disturbance, but just within the range of those defects themselves, the crests. So I would say at this area out here in the middle, which we're measuring right in the middle, I think that we would be getting a true estimate of the erosion that's happening in the neighborhood of the meter. And this is it's not a new field approach either. People have been using micro erosion meters in various forms for decades. Do you have any more questions? See?
This is Missy Epps. I have a question or two. Can you hear me?
Cool.
I'm having trouble hearing you. Yeah.
Okay, I'll type it.
Why don't you just unmute?
Can you hear me? I am unmuted.
Are there any questions in the room audience that you'd like to ask?
I had some questions about the erosion rate. Just curious about the technique. How does it work? What is the depth of measuring? The depth change.
Okay, so I did not bring the actual micrometer in with me, but I can pull up that slide and that'll be easier to. Yeah. Too far. There. Okay. So the micrometer I'm holding in my right hand, and the picture on the right is calibrated to 1/1000th of an inch, and came with like the NIST certificate of calibration.
Probes down into his touching surface.
Exactly, yeah, it sits, there's a completely flat machine part that sits in here, and then, a little probe kind of, but it's like a very smooth stem, it just goes through the hole.
Yeah, I didn't know if that was using on the lasers.
No, it's a completely analog micrometer.
And how many, they said you data were inclusive for all sites, or how many sites? It looks like it's a bit of a challenge to get these set up. not making a huge challenge, but
Yeah, we only installed one at a time, which is why there's different lengths of time at each site. So there are 4 sites, and we have not been back to site 4 since it was installed. Like the plate that we used to install it is still in the cave. And we got report from the park that there was, there were recently some really big storms, and there's been a lot of sediment piles shifting and all kinds of exciting activity. So it'll be interesting to see next time we get back on.
why did you, I those things seem like they're going to be higher erosional rates or it's randomly?
So we're looking for scallop bedrock on the floor of a passage in an active river, which, put us down to a pretty small set of locations to begin with. And then the fact that this one is not very far from Old Tour Trail. It's relatively accessible as cave field sites go. It's like 2 miles of hiking in the cave and then just a little bit of wading in the river to get to it. So, so the combination of having those qualities and being not too hard to get to. And also to be able to give other people directions for how to get there. I'm storing all of this data on Pangea so that this project can, continue indefinitely. Yeah, you're welcome. Yeah, see, we have.
So, John Martin asks, can you speculate a bit about the event on the surface that may have caused Mount Ararat?
Right. So we're uncertain about that. It could have been a landslide. Let me go to that map. So on the top of this map, you can see the profile of the modern topography in a dark line, and then the hypothesized previous surface in dashed lines. And so we're assuming that there was some kind of cave entrance there, and then there may have been a landslide that initiated these debris flows, or it could have been a ponded sandstone floored sinkhole that collapsed and released all this material in, or there could have been a surface stream that in an extreme flood provided these materials into the cave. We really don't have enough surface evidence to narrow down between those 3 possible scenarios. Great.
Tom Bile says, just curious, different clays can expand when wet and dry. Can expand when wet and shrink when dry. Is the clay in Mammoth Cave this type, or does it maintain a constant size when wet and dry?
I have not done any clay mineralogy work on material in Mammoth Cave. So I can't speak to that. I'm familiar with that phenomenon and with clay mineralogy, but I didn't do any XRD on the sediments or anything.
Missy Epps asks, can you please walk us through the logic of how distance traveled of a particular particle scales with erosion rate? I would expect instead for erosion rate to scale with number of particles impacting a particular location. Also, it seems that sediment concentration is a very transient time variant property. How representative were the 2 cited studies of long-term range of variability, i.e. what were observation time periods?
Wow, that's a lot of questions. So this, let me kind of start with the disclaimer that this project, the erosion modeling is still in process. So any suggestions? Maybe Zeke, you could save the chat and like email it to me afterwards. I would really like to have those questions in writing to be able to address as we go forward, and refine the analysis. So the first question was pertaining to relations between erosion rate and travel distance. And so I think to be so much easier, missing, right? I think what you're referring to here is the fact that I showed first the erosion rates from, beginning after the third bounce of rains, and then later the erosion rates for particles that travel more than 1 meter. And so that second set for the particles that travel more than 1 meter, those plots are like hot off the press last week. And so what I'm trying to do there is dial in the contributions to erosion from particles that are not being just deposited early on. So I want to make sure that I'm capturing a true erosion rate from particles that would continue to be transported. And so that was part of that, trying to select the right subset of particles that are contributing to erosion. Perhaps she can chat to you to let you, or she can unmute herself. I don't know.
Yeah, I can hear. I see. I see. That makes sense. I understand now what you're trying to get at. So it's not so much that it's scaled with the. Can you hear? So anyway, no, that answers my question.
Oh, awesome.
And the second question was a different question about your sediment concentrations being a really transient characteristic. And the two studies that you cite, I was just curious how representative they actually were of the long-term range of variability of sediment concentrations. It seems like you could have large events with really high concentrations, sort of the catastrophism of abrasion, erosion of scallops, if you will. Were those studies you cited? What was the time scale of those studies?
Okay. So those, can you write your, thank you. Each of those studies were, I think, on the order of a year or two long. The Logston River was from a master's thesis, and the Arch Spring is from Ellen Herman's PhD dissertation. So the thing is, there aren't a lot of studies of sediment concentration in cave rivers, and so that's the data set that we're looking. That's kind of the pool of data that I had to work with to compare that. The reasoning behind my wider range of simulated concentrations was I used 0.015 as my high end from Lam et al. 2008. It's like a very high concentration. And then I used that 7 times 10 to the minus 6, which was a low measurement from Ellen Herman's. So there's just, not the quantity of data to really be able to answer that question, I think, right now.
So I think those studies then are minimums probably, because if you were to measure continuously over longer time periods, you're going to capture larger concentration events. I'm basically saying your work is probably more important than you're giving it credit for.
Well, thank you.
Some
Oh, yeah, I think that that's kind of a, an optical illusion. Sometimes if you stare at them long enough and with the shadows hitting just the right way, they will look like convex forms, but they are, yeah, cave scallops are as I run through all of the things I've seen, really pretty much exclusively, concave. Um, I'm not sure. So in my model does not explicitly incorporate dissolution into it. So I'm doing an abrasion modeling and then comparing my results with previous studies with dissolution. So I did not vary any of the chemical parameters they used.
Is this gonna be-
That's possible. Yeah, there could be surface geophysical techniques done in Doyle Valley, and so then we might be able to get a better idea of the depth to bedrock on the surface, and we might be able to find evidence of, previous landslides or, it's like that. That's a neat idea. More questions from chat or room?
One more question. Do higher elevation sediments, as in crystal onyx cave, show the same sorting as the ones in your cave, I'm assuming?
Who's asking that?
Roger Brucker.
Ah, awesome. Yeah, so that that would segue nicely into the project that is still underway this summer, which we have been looking at crystal onyx cave, and we've been looking at surface sediments and trying to tease out some of that paleo flow. So yeah, we can chat about that over a beer sometime, Robin. I don't have any more chat questions.
So are there other?
Looks like Abby has. Yeah, so there are sediments nearby Mount Ararat that have been dated to 1.2 million. So not from the deposit itself, but nearby. So that was done using cosmogenic burial dating, and so then we take that as evidence for that's the last time that area was active as like a main river pathway. So we then think that Mount Ararat would be younger than that age. That's why, yeah. That's the premise behind the burial dating, is that they were exposed on the surface and then deposited in the cave, and then you look at the difference between the aluminum 26 and the ratio between 6 and beryllium 10, And because they decay at different rates, then you're able to determine how long it's been buried.
Well, in that case, I think what we should do is give it. And then, other than faculty committee member. So there's something that you know about.
Road room. Will be food and drink.
Okay. Awesome. So